Okay, we've got the scope hooked up. The signal is coming into both channels. We are using a T fitting to jump both channels together. We're feeding the signal from the signal generator, and right at the moment we are running about 10 hertz. Turn that down just a fraction. Alright. Anyway, we're right now set at 0.1 seconds per division. And if we were 1 second per division and running at 1 hertz, then you would have 1 cycle every division. If you are at 0.1 seconds per division, that's 1/10 of that, which means that in order to have 1 cycle every division, you have to be running at 10 cycles per second. So we are right now seeing that the oscilloscope is dancing with its the peaks of the triangles hitting right on the radical bars every division. So we are tracking that 10 hertz very well at this 0.1 seconds per division. Now if we go to 50 milliseconds per division, then we should be able to see half as many peaks, because we have half as much time per division. And across 10 divisions, that means instead of 10 cycles, we're going to be able to see 5. So we count the peaks, we see 1, 2, 3, 4, 5 peaks with this 10 cycles. If we go to 20 milliseconds per division, we should have 1/5 of the number of peaks that we had at 0.1 second per division, and we do at 10 cycles. We have 2 full cycles, and we can adjust the position of that and the triggering point so that you can see that it is exactly 2 full cycles right there. Okay. If we go to 10 milliseconds per division, we're spanning the whole thing. And at this point, okay, with the running at 10 cycles per second and 10 milliseconds per division, we are seeing 1 full cycle happening because we're sending it across this line here. 1 full cycle on both sweeps. We can now kick ourselves up a decade and position this just a hair, and you can see that we are hitting right on the graticals. 10 peaks. We are at 10 milliseconds per division and running exactly 100 cycles per second. At 100 cycles per second, we have 1 cycle in every division. There we can see it right on the division line. If we go to 5 milliseconds per division, we're running 1/5 of that. We see the 5 peaks again. 5 full peaks. 1, 2, 3, 4, 5. 2. Right about there. 2 full cycles. Oops. 1 millisecond per division, we see 1 full cycle. We now kick ourselves up another decade, and we want to go to 1,000 hertz. There's 1,000 hertz. And we see that we are, once again, right on the division lines, 10 cycles across. If I go to 1/2 of that time per division, we see 5 cycles in that period. And if I go to 1/2 of that, sorry, 1/5 of that, then we get 2 cycles per division. And if I go to 0.1 milliseconds per division, in 10 divisions, that's 1 millisecond, which means we get 1 cycle, and with 1,000 cycles per second, we get 1 cycle across the screen. If we now kick ourselves up again another decade, we are at 10 kilohertz, and we are seeing here we're hitting right on the division lines again, all the way across. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 divisions, 10 cycles. If I go to half of that time per division, then I'm going to get half of those peaks. I get 5 peaks across the screen. Yeah, that would be right. If I go to 20 milliseconds per division, that's 1/5 of 10, which is 2 cycles. And once again, we have 1, 2. If I go to 10 microseconds per division, then I'm not sure if I was saying microseconds earlier, but it's microseconds per division at this point, and we are running 1 full cycle in 10 microseconds at 10 kilohertz. And I can kick this thing up again another decade. Right there. So we are now running 100 kilohertz. And we are doing it at 10 microseconds per division, and we now have 10 divisions across the screen. And if I go to 5 microseconds per division, that would be half of the time, so therefore half of 10 cycles, so we get 5. If I go to 2 microseconds per division, that's 1/5 of the time. 1/5 of 10 is 2 full cycles. We've got that. We go down to 1 microsecond, and what we see is we have 1 cycle. With 100,000 hertz, we have 1 cycle across this 10 divisions at 1 microsecond. That's because that's representing 10 microseconds, and 10 microseconds is what 100 kilohertz would take. Now, if I kick myself up another decade, it's about as close as I'm going to get megacycle. And what we see is, once again, we'll just adjust the triggering so we can see it easily. We are right on the gradical in every case, all the way across. If I lower myself to 0.5 microseconds per division, that is 1/2 of the time. Again, we get 5 peaks. 1, 2, 3, 4, 5. If I go to 0.2, adjust my positioning a little bit here. There we go. 1, 2 divisions, 2 cycles. So we are doing well at 1 megacycle, and if I go one more step, we now wind up in the Lissajous position, which with triangle waves, you kind of get a square here. If I go to a sine wave, you get the familiar oval. And like I showed you earlier, I can change the position with my channel 2, I go horizontally, and then channel 1, I can go vertically, and I can center that thing if I want. And everything is working great. Our time base tracked perfectly from 0.1 seconds per division all the way down to 0.2 microseconds per division. Tracked perfect. Okay, what we're going to do at this point is to try and determine the bandwidth of the scope. And what we have right now is 1 megahertz signal coming in, and it's adjusted for 20 millivolts per division, so that we get 40 millivolts up, 40 millivolts down. what we should see, if we drop 3 dB at any point, then we should drop to 2.78 divisions. And if we don't hit 2.78 at 30 megahertz, then we've exceeded or met the rated bandwidth of the scope. Right now, what we're going to do is we're going to use this 100 megahertz B&K as our reference scope. And it also is at 20 millivolts per division. And there we go. I will drop the illumination of the scale. Let's get this out of the way. And we'll raise that a bit so it's maybe a little easier to see. Alright, we're running exactly 4 divisions up and down. Looks like my center's drifted just a hair here. Check it again. Alright, we're 4 divisions up and 4 divisions down exactly. I know it's difficult to see on this camera. Sorry about that, but now I'm going to take the signal and I'm going to put it in on my B&K, and we're going to observe where we're at here. And what I see is I am just about touching the bottom 4 and the top 4, so I'm the same as my reference scope at 1 megahertz. I've got 4 up and 4 down. I can kick this up a little bit too, makes it just a hair easier maybe to see. Okay, so now we're going to go back to our reference scope, and we're going to kick this up to 10 megacycles. Alright, that should be about 10, and alright, we're measuring 10 megacycles right now. And we're going to disconnect that counter because we don't want the capacitance to load our system. We only wanted it to measure our frequency response. Okay, let's put this back on. Alright. And once again, we adjust our output to give us exactly 4 up and 4 down. And that would be it right there. That's exactly 4 units up and 4 down at 10 megacycles. We go back to our B&K. And what we see is that we are about 0.2 divisions down both top and bottom. So we've dropped 2.2, 2/10. And I go back to our reference scope. This reference scope has 3 times the bandwidth of this B&K, so I feel safe working under 30 megahertz with this thing. Okay, now what we're going to do is we're going to kick our generator up. Let's see, we've got to hook our counter back in again so we can see what we're doing. Alright, and we're going to kick our counter up to the 20 megacycle range. That's 20 megacycles, close enough. All right, and we disconnect the counter again. once again come over here and we adjust our output of the generator so that we get exactly 4 up and 4 down. And that would be it right there. Okay, now we take that lead and we move it back to the B&K. And at 20 megacycles, we see that we have fallen 0.2, 0.4, 0.6 divisions from the top, and we've risen 0.4 divisions from the bottom. Let's double check our ground to make sure we haven't drifted. Okay. And 0.4 from the top, 0.4 from the bottom at 20 megacycles. All right. And let's go ahead and try 25. Let's see, we're going to have to put this back on here again. I think my scope will do at least 25, or my generator will put out at least 25. All right. All right, there's 25 megacycles right there. Let's disconnect the counter, take the capacitance out of there. And all right. And let's move our lead back over to our reference scope. And looks like we've fallen in our output. So let's raise this output once again so that we have exactly 0.4 divisions up and down. It's like every time I get away from that, it raises. Okay, once more. All right. Well, again. There. That's exactly +4, -4. 25 megacycles. All right. And what we see here is that we have fallen 2, 4, 6, 0.7 from the top, and 2, 4, 6, 8, closer to 0.8 from the bottom. So yeah, 0.7, 0.8 divisions we've dropped. We're going to have to put in 30 megacycles to see if we hit that 2.78 mark. Alright, what I've done now is, in order to get to 30 megahertz, I'm using this B&K E200D RF generator, and I've got it tuned into 30 megacycles, and I am adjusting the output of that generator to give me 4 divisions up and down. But in order to do that, I had to reduce myself to 10 millivolts per division, so I went down a level here, and I had to do the same on my B&K so I can match it. And we've now adjusted the peak-to-peak height so that we are up 4 and down 4 and just touching the gradical on our reference scope. And if we move this to our B&K, then you can raise the intensity so it's easier to see. And what we see is that we have dropped now 1 full division, and we are down 0.2 more, so 1.2, and same on the bottom, we are up 1.2. So we have 2.8 divisions up, 2.8 divisions down. So we are right at the bandwidth. We are at 30 megahertz. We are meeting the bandwidth 3 dB point. All right, so 20 times the log to the base 10 of 2.8 over 4, 2.8 divisions over the 4 expected, is equivalent to a negative 3 dB. And so if we hit 2.8, we've gone down 3 dB on this scope. And on channel 1, it certainly appears, channel A, it appears that that's exactly where we are, is 2.8. Now if I move this input to channel 2 and adjust accordingly, like just go to channel B, okay, there we go, and make sure that we're zeroed exactly, and we are, and let's go ahead and connect up. And what we see is that at the same 10 millivolt per division scale, we actually are a little more improved on our bandwidth on channel B. So we are down 0.8 and up 0.8. So instead of being 1.2 plus and minus, we are 0.8 off. A little bit better bandwidth. Well, there you have it. BK1479B 30 megahertz oscilloscope in beautiful condition. Not an objectionable blemish on the entire surface of the unit. Everything functions perfectly. We passed all of the calibration checks with flying colors, including our bandwidth, and I'm just very proud to offer you this. It will come with a brand new set of probes, and we have an excellent service manual, and if you can get a look at the just the heft of this, there are, I don't know, approximately close to 200 pages, I think, because not only do we have all of the user information, calibration information, but we also have parts lists, and then we have our schematic diagrams in both 8.5 by 11 size, or an even more usable 11 by 17. I prefer the 11 by 17 myself because I'm getting older, my eyesight's not as good as it used to be. This makes it much easier for me to see, so I figure I'd share that with you. And just putting this book together alone took about an hour and a half, took nearly a ream of paper. You figure that out, and this book is easily worth $30, $40, somewhere in there. So you'll get an excellent service manual, a wonderful set of probes. Probes are worth about $14, $15, and a marvelous scope. So happy bidding, and thank you for listening.